Alright, welcome back to PyCSE. This is another video on mathematically informed machine learning, and the idea today is we are going to look at a periodic regressor, a neural network with guaranteed periodicity, so that we can model and fit periodic data and extrapolate in a periodic way. This is not a feature of normal neural networks with tanh or sigmoid or ReLU. Those will saturate far from the data, and it may get partially periodic in the data set, but it will not extrapolate periodically. And I'll show you today that we can get that. So the idea again is to use something like a Fourier feature expansion, and we just embed periodicity into the architecture, and that gives us periodic neural nets. So we want this in applications where periodicity is important. You wouldn't pick this model for non-periodic data. You would use this because you know there's periodicity and you want to get it. So we see this all the time in time series, in physics, in materials. There's lots of places where periodicity becomes relevant. The other thing we can integrate in, as with others that I've showed you, is this LLPR uncertainty quantification. Again, this is a modified delta method on the last layer, which gives us, you'll see, reasonable looking uncertainty quantification at very low cost. So this is a feature in PyCSE. You load the JAXPeriodic module, you get the JAXPeriodicRegressor. This is an sklearn compatible regressor, and so we'll have .fit, .predict, and compatibility with all of the sklearn pipelines and pre-processing, etc. So you can read through this notebook. I'll have a link in the video description. But the gist of it is that we have data and we can take combinations of signs. We might get some complicated feature here, but each neuron is sort of an expansion in this space, and we can use it to learn periodic data. So here's our first example, some random data. It's just a sign right now with some random noise in it. We build a regressor, 2 layers here. We have 2 options. We can define the periodicity if you know what it is, or you can fit it. I'll show you that later. And then you call model.fit, and then we use training, and you can see here the calibration. You want to see this number being fairly small. That means if it's too large, then we don't get a good estimate of the noise. If we test this, you can see here this green bar is where we fit, and this model is probably overfitted with the wiggles in here, but the main point that I want to show you is in extrapolation behavior, that because it's periodic, it extrapolates with the right period and has the same features that you see inside of it. And that's something I'll show you again later is not possible with a normal regular neural net. So we build in the extrapolation behavior and the function behavior we want into our model, and that's what I mean by mathematically informed. We don't simply take a black box and hope for the best. We choose properties of the model that we want, build it in with guarantees, and then we get what we need. Okay, we can capture more complicated periodic patterns, anything that it looks like a sine, or that you can use a Fourier series. Here we have some other kinds of wiggles. We can fit with 1 harmonic or 3 harmonics, various numbers of features that allow us to capture the periodic neighbors. And you can see as you add more and more harmonics, you get more and more evidence of overfitting in the noise here. And so this is a way you can regularize or control the amount of wiggles. We can also mix things. We can have mixed periodic and non-periodic features. So what we have in here is our mixed data, and then we have some only the angle here is periodic, so we can define among the dimensions which ones are periodic, and we use a dictionary here, so only the first one is. And if we scroll down to the visualization, you can see that the angular dependence is periodic, but the other one is not periodic. It has a fixed angle. So we can combine those and get very sophisticated models that treat the periodic part with periodicity and the non-periodic parts with no periodicity. We have the uncertainty quantification. Again, this allows you to put confidence intervals on your fits, and that gives you some uncertainty, ability to estimate reliability, which is pretty nice. This one is just an application in computational chemistry, looking at a potential energy as a function of torsion angle. I'll probably skip through this. You can see we have another one of these like complicated periodic behaviors, and we have uncertainty and errors associated with those predictions in here. If we ignore the periodic nature of data, let's just scroll down to the figure here. So let's say we have this data. If I was to fit a regular, probably ReLU network here, then you can see it extrapolates linearly outside of the training region. And that's because we don't have any data there to constrain the model. And if we use our periodic model, you see it goes in the right way periodically. Not because we have data out there, but because we constrain the functional form to have periodicity, and we fit the periodicity with the data that we have. So that's a benefit of this particular approach when you know periodicity is important. There's sometimes you don't know the exact period, and that is something you need to fit, and we support learning that period from data through the argument learn period equals true. And this is a little more challenging because there's noise and you don't know what the true period is, but you can use this to learn what a period might be. And here is an example where we learn the period in addition to fitting the data. So the period is a trainable parameter, and you need a pretty good initial guess. You know, we guessed 6, it learned something close to 5. The true value here was actually 5, so it did a pretty good job. And finally, it's fully compatible with sklearn. You can create pipelines, you can use scalars, you can do feature generation, you know, whatever features of sklearn you want. It is easy to get, and then you get the easy access to scores, setting parameters, everything like that. So that's it. You can find this on GitHub in the PyCSC repo, and it rounds out the mathematically informed versions where we can design in monotonicity, we can design in convexity, we can design in periodicity, we can design in mixed integer representable, and those are the mathematically informed machine learning models that are available in PyCSC. So I hope you like it, and we'll see